Okay. Okay, good afternoon. I'm Luca Orusa, PhD student from the University of Torino, and I'm here to present my new work titled New Determination of the Production Cross-Section for Secondary Positrons and Electrons in the Galaxy. And this work has been done in collaboration with Mattia Di Mauro, Fiorenza Donato, and Michael Korsmeier, and has been recently accepted for published on Physical Review. During the last years, the IMSO2 experiment, but also Pamela, Dampe, and Khaled has performed really precise measurements of the electrons and positron flux. And these particles are first of all produced by the interaction of cosmic rays with the interstellar medium. And this is the so-called secondary contribution. In order to disentangle between secondary contribution and the production from astrophysical sources or new physics sources, we have to provide really precise prediction on the secondary production. And in particular, the source term that describe the secondary production of these particles can be described with this formula that enters in the propagation equation, where you see that there is this term, the sigma over the T, that is the energy differential production cross-section of electrons and positrons from the interaction of a nuclei I over a target J. If you collect all the available parameterization that are still used today for the production of electrons and positrons from the interaction of a proton over hydrogen collision, you can basically obtain a factor of 2 of uncertainty on the total normalization of the secondary positron flux. The idea of this work is then to use the data provided by different experiments in order to reduce this uncertainty. And in this talk, I will concentrate on positrons, and positrons in a proton-proton interaction can be produced by the decay of all these different particles that are listed in this really scary picture. And in this work, we basically considered different experiments at different center of mass energies, and usually experiments provide data as Lorentz invariant fully differential cross-sections that can be described with this formula. And basically, we then repeated the same type of analysis also for electrons. So we start from the fit to the pi plus data, that is the main channel of production of positron. To perform the fit, we developed a formula that for the Lorentz invariant fully differential cross-section that has this structure, where you see that there is this term sigma 0 that is the total proton-proton inelastic cross-section. Then we have just a normalization factor, and then you have these two functions fp and fr that are two functions that take into account effectively of the different possible production mechanism of pions, so the classical prompt emission or the decay from some hadronic resonances. And these two functions depend on pt, that is the transverse momentum, and xr, that is a quantity that is defined as the energy of the pion divided by the maximum energy that a pion can have in a proton-proton interaction. And then we modify the behavior of our function with respect to the center of mass energy with an additional function A. So basically, we perform a two-step fit. In the first step, we perform a fit to the data provided by the Na49 collaboration at a square root of S energy of 17.3. That is a strategic energy for secondary positrons. And basically, in this first step, we perform a fit to all the parameters that we assume that are scale invariant, and so they do not vary with square root of S. And we decided to tune most of the parameters on this data set, since the data provided by the Na49 collaboration cover a huge range in the kinematic space that is interesting for us. And we obtain a good fit, and we find that for our model, that the uncertainty band at the 1 sigma level is at about 5%. Then we fit all the other parameters that encode the variation of our model with the center of mass energy of the interaction, performing a fit to the data provided by the CMS and ALICE collaboration at really high square root of S energies, combined together with the measurements of the multiplicity of production of the pi plus at small square root of S, in order to have a complete model from low to really high energies. And we found total uncertainties between 5 and 10%. And so now we have basically a complete model for the Lorentz invariant fully differential cross-section of the pion that we can integrate above the solid angle in order to obtain the sigma in the T for the pion. And this quantity has to be convoluted with the probability of decay of a pions into a positron. So pions decay into muons, they decay into positrons, and for the first time in literature in this field, we considered also the next to leading order correction of the muon decay into positron. Then we have to consider also all the other channels. In particular, we have chaos that can contribute at the 10% level of the total cross-section. And basically for chaos, we reproduce exactly the same analysis that we have done for pions, finding really similar results also for the uncertainties. And then we considered all these decay channels that are here listed that can actually produce a positron in the final state. Then we have a lot of other channels. In particular, positrons can be created from the decay of pions that are produced by the decay of some strange particles. In particular, we have the K0s that, and we estimate the contribution from the K0s performing a fit to the available data provided by the Na61 collaboration at a square root of S energy of 17.3, combined with the measurements of the multiplicity of these particles, while the contribution from K0L is obtained through a rescaling of the contribution of the K0s, because we do not have available data for of the cross-section for the K0L, and we made this assumption after that we checked that the energy distribution of positrons produced by a K0s or by a K0L in a proton-proton collision is basically the same, with just a difference in the normalization, and this difference in the normalization is connected to the different branching ratios of the decay channels of these two particles that can produce positrons in the final state. Then we have the contribution coming from all these other particles that have for which we do not have available data in the energy that is interesting for us, and also all of them have a mass that is quite similar to the lambda baryon. And so for these type of particles, we assume that the contribution of these particles to the positron cross-section is basically is equal to the contribution of the lambda to the electron cross-section with a normalization factor. In fact, the lambda can decay into a pi minus and so produce an electron in the final state. And this rescaling factor is estimated through PTA Monte Carlo generator, and is basically a combination between the multiplicity of production of all these different particles with respect to the lambda, combined together with the branching ratios of the decay channels of these particles that can produce positron in the final state. And then we also consider the contribution of coming from the pi zero to the positron cross-section that is at the percent level, that is estimated also in this case, assuming that that basically the contribution from the pi zero is equal to the one from the pi plus. After that, we check that the energy distribution of positrons produced by a pi zero or by a pi plus in a proton-proton collision is basically the same, of course, with a huge normalization factor that make possible that the pi zero can contribute only at the percent level. So now we have all the elements to compute the final the sigma in the T for positrons, and you can see how the most important contribution is the one of the pi plus, while chaos can contribute at the 10% level, and all the other subdominant channels can contribute at a few percent level. And the main comment of our results is the really small uncertainty band that we are able to find thanks to the really high precision of the data that we found in literature, and that's it. And this true function and this plot are obtained for the true incident proton energies of 10 and 100 GeV. Until now, we have just considered proton-proton cross-sections, but of course, in the galaxy, we can have also nuclei-nuclei interactions that can produce a lot of positrons in the final state. To estimate the values of the cross-section for this type of reactions, we performed a fit to the data provided by the Na49 and Na61 collaboration at these two square root of S energies. This experiment performed a proton over carbon collision. And to perform this fit, we assumed that the Lorentz invariant fully differential cross-section for a proton over carbon collision is equal to the one of a proton-proton interaction with a normalization factor that is connected to the mass number of the nuclei that are present in the interaction. And in the case of pions also, we consider a reshape of our proton-proton cross-section due to possible asymmetries between forward and backward production that can arise in a nuclei-nuclei interaction. So now we can compute the source term that is obtained through a convolution between the values of the cross-sections together with the fluxes, the primary fluxes of cosmic rays, and the gas density of the interstellar medium. And Also for the final source term, we find really small uncertainties, and one important result is the fact that the channels that involve helium can produce a contribution between 30 and 40%, so quite a lot, while the heavier nuclei can contribute at a few percent level. And then we repeated the same analysis also for electrons, finding really similar results. So to sum up, we determined through analytical description or referring to Monte Carlo generators the inclusive cross-section to the contribution to the positrons or electron cross-section coming from all these particles. All our results are available, and you can use them, and you can find them at this link where we have all the table for different electrons and positron energies and incident nuclei energies. And for sure, our results could be improved if in the near future also proton over helium interactions will be performed, since as I showed you, the helium channel has quite a great importance in the computation of the source term. And then I just want to remark again that our major results reside in really small uncertainties that we found from the global analysis. Thank you for your attention.